Welcome to Module 702. In the previous session, we examined the fundamental causes of urban heat islands, exploring how dense urban structures, limited vegetation, and vast expanses of impervious surfaces such as asphalt, concrete, and rooftops interact to trap solar energy. We saw that these factors create a significant divergence between urban and rural temperatures, with densely built neighborhoods often several degrees warmer than surrounding rural areas. We also discussed the human and ecological implications of elevated urban heat, including increased energy consumption for cooling, heightened health risks, and impacts on urban biodiversity. Vulnerable populations, such as the elderly, children, and individuals with pre-existing medical conditions, are particularly susceptible to heat-related health issues, including heat exhaustion, heat stroke, and exacerbated cardiovascular or respiratory conditions. Today, we shift our focus from problem identification to solutions. Cities around the world are actively exploring interventions to mitigate urban heat through thoughtful urban design, strategic material selection, vegetation implementation, and careful planning of urban form. These strategies aim to reduce temperatures at both micro and macro scales, improve human thermal comfort, enhance urban livability, and reduce energy demand. In this module, we will analyze interventions ranging from large-scale solutions, such as ventilation corridors and urban greening initiatives, to micro-scale strategies, including tree shading, reflective pavements, green roofs, and water features. By understanding the principles, effectiveness, and appropriate contexts for each intervention, we can develop holistic solutions that maximize cooling and resilience across diverse urban environments. Urban areas are experiencing significant warming due to the combined effects of global climate change and the urban heat island phenomenon. Global climate change has raised baseline temperatures, increased the frequency and intensity of heat waves, and extended periods of elevated temperature. However, the UHI effect intensifies these conditions locally. Urban surfaces such as asphalt and concrete absorb solar radiation during the day and release it slowly at night, leading to higher nighttime temperatures compared to rural areas. Building density and street geometry further restrict airflow and limit convective cooling, while the absence of vegetation reduces evaporative cooling potential. Urban areas can be up to 5 to 10 degrees Celsius hotter than surrounding rural zones during extreme heat events, particularly in dense mid-rise and high-rise neighborhoods. The consequences of elevated urban temperatures are severe and multifaceted. High daytime temperatures reduce productivity and cognitive performance, affect physical health, and increase the likelihood of heat-related illnesses and mortality. Heat stress is particularly pronounced among vulnerable populations, including children, the elderly, and those with chronic diseases. Elevated urban temperatures also increase electricity demand, straining energy grids and contributing to greenhouse gas emissions. Urban heat reduces outdoor activity, impacting social well-being and mental health, while also exacerbating air pollution by accelerating the formation of ground-level ozone. Urban cooling strategies address these challenges by reducing daytime overheating, supporting nighttime cooling, and improving human thermal comfort. Shade, reflective surfaces, vegetation, and water interventions lower surface and air temperatures, enabling safer and more pleasant outdoor environments. Reduced energy demand for air conditioning provides cost savings and decreases greenhouse gas emissions, while integrated interventions enhance overall urban resilience. Implementing these solutions is essential for ensuring livable, healthy, and climate-adaptive cities, capable of coping with current heat extremes and future temperature increases. In this module, we focus on three main categories of urban cooling interventions: vegetation, materials, and urban form. Each category functions through distinct physical mechanisms. Vegetation provides shade and cools the surrounding air through evapotranspiration, a process that absorbs heat energy when water evaporates from plant surfaces. Materials influence reflectivity, thermal mass, and heat conductivity, determining how much heat surfaces absorb and how quickly they release it. Urban form affects shading, airflow, and heat retention within street canyons and around buildings. Effectiveness depends on local context. Climate, street orientation, building density, and human activity patterns all determine how well a strategy works. For example, high-albedo surfaces reflect sunlight effectively in arid climates but may have limited impact in shaded, humid streets. Similarly, vegetation can provide significant cooling in dense urban districts but requires careful selection of species, soil volume, and irrigation. Understanding the principles behind each approach allows planners to implement context-sensitive solutions. Combining strategies creates synergistic effects, where interventions reinforce each other to produce greater temperature reduction, enhanced thermal comfort, and stronger urban resilience. Vegetation is one of the most effective natural cooling tools in cities. Trees, shrubs, and plants provide shade, reducing the direct heating of pavements, streets, and building surfaces. Shaded surfaces can be several degrees cooler than unshaded areas, significantly reducing thermal stress for pedestrians. In addition to shading, vegetation cools the surrounding air through evapotranspiration. Water evaporates from plant leaves, absorbing heat from the surrounding air and lowering ambient temperatures. Depending on species, canopy density, and local conditions, evapotranspiration can reduce ambient temperatures by 2 to 4 degrees Celsius or more in dense urban areas. Vegetation also provides ancillary benefits. It improves air quality by filtering particulate matter and pollutants, reduces noise pollution, enhances urban biodiversity, and contributes to mental well-being and aesthetic appeal. Properly designed green spaces create comfortable microclimates that encourage outdoor activity, enhance social interaction, and contribute to a sense of community. Vegetation mitigates urban heat island effects at both microclimate, streets, plazas, and neighborhood scales, helping to moderate daytime temperatures and improve nighttime cooling. Cities employ a variety of vegetation-based interventions. Street trees and tree-lined boulevards shade sidewalks and streets, benefiting pedestrians, cyclists, and vehicles. Urban parks and larger green spaces act as cool islands, creating local zones of lower temperature compared to surrounding built-up areas. Green roofs and vertical green walls extend vegetation coverage to building exteriors, rooftops, and facades, providing cooling where ground space is limited. Small-scale interventions, such as pocket parks, planter boxes, and rain gardens, significantly enhance comfort in dense districts. Even narrow green strips along streets lower air temperature, reduce radiant heat, and improve pedestrian thermal comfort. Vegetation interventions also enhance biodiversity, manage stormwater, reduce noise, and increase the visual appeal and livability of urban areas. Effective vegetation implementation requires careful design. Canopy density, species selection, and growth patterns determine shade provision and cooling potential. Soil volume and quality are critical for sustaining healthy trees, especially in confined urban spaces. Adequate irrigation and water management are essential in hot or dry climates to maintain evapotranspiration rates. Strategic placement is crucial. Vegetation should target high-exposure areas such as busy streets, transit stops, plazas, and playgrounds to maximize cooling where thermal stress is greatest. Properly designed vegetation interventions optimize pedestrian comfort, reduce urban heat island intensity, and improve urban livability. Urban materials play a fundamental role in shaping the thermal environment of cities, because they directly determine how heat is absorbed, stored, and released over time. Every urban surface, from streets, sidewalks, and plazas to rooftops and building facades, has specific physical properties, including color, reflectivity, thermal conductivity, and heat capacity, that govern its interaction with solar radiation. Dark and dense materials, such as asphalt or traditional concrete, absorb large amounts of solar energy during the day, and release this heat slowly during the evening and nighttime hours. This delayed heat release keeps urban surfaces and the surrounding air warm well after sunset, contributing significantly to the urban heat island effect and prolonging thermal exposure for city inhabitants. In contrast, materials with higher reflectivity and lower thermal mass interact with solar radiation differently. High albedo surfaces reflect a larger portion of incoming sunlight, limiting heat accumulation during the day, while low thermal mass materials cool more rapidly once solar input decreases. These material properties influence not only surface temperatures but also near-surface air temperatures, nighttime cooling rates, and overall urban thermal balance. As a result, material choice is a critical component of urban heat mitigation. By influencing how heat is absorbed and released, urban materials affect pedestrian comfort, nighttime heat retention, and energy demand at the building and neighborhood scale. When considered as part of a broader urban design strategy, materials provide a powerful lever for improving thermal conditions in cities facing rising temperatures. Building on these physical principles, cities can actively reduce urban heat through targeted material-based interventions. High albedo pavements and roofs are among the most widely used strategies, as they reflect a significant share of incoming solar radiation and remain cooler than conventional dark surfaces. By reducing surface temperatures, these materials limit the amount of heat transferred to the surrounding air and improve thermal conditions at street level. Cool roofs and reflective coatings applied to building exteriors further reduce heat storage in walls and roofs. By lowering heat transfer into indoor spaces, these measures decrease the demand for air conditioning, reduce energy consumption, and limit the release of waste heat back into the urban environment. Permeable pavements introduce an additional cooling mechanism through water infiltration and evaporation. When moisture within the pavement evaporates, it absorbs heat from the surrounding surfaces and air, creating localized cooling effects that enhance pedestrian comfort. Low thermal mass materials support these strategies by minimizing long-term heat storage and allowing faster cooling during nighttime hours. When implemented strategically and in combination, material-based interventions can produce synergistic cooling effects. For example, reflective pavements combined with adjacent vegetation provide both reduced heat absorption and shading, resulting in more comfortable urban microclimates. Through the coordinated use of high albedo surfaces, cool roofs, permeable pavements, and appropriate material selection, cities can effectively mitigate the urban heat island effect and enhance resilience to increasing heat stress. When implementing material-based cooling strategies in urban areas, practical and context-specific considerations are essential to ensure long-term effectiveness and sustainability. First and foremost, materials must be durable and maintainable, capable of withstanding daily wear and tear from pedestrians, vehicles, and weather conditions. High-quality pavements, roofing materials, and coatings not only provide reliable cooling benefits but also reduce maintenance costs over time. Cost-effectiveness is another important factor. Cities need solutions that deliver measurable temperature reductions while remaining affordable to install and maintain, especially when applied over large areas such as streets, plazas, or public housing complexes. While high albedo surfaces and reflective coatings are highly effective in reducing heat absorption, they can sometimes produce glare, affecting both pedestrians and drivers. Careful selection of material finish, color, and surface texture is necessary to balance thermal benefits with visual comfort and safety. Moreover, material interventions are most effective when integrated with other cooling strategies. Combining reflective pavements with vegetation, shaded walkways, or strategically oriented buildings amplifies cooling effects, creating comfortable microclimates and enhancing pedestrian comfort at both street and neighborhood scales. Local climatic conditions also influence which material strategies are most appropriate. In hot and arid climates, reflective surfaces and low thermal mass materials are particularly effective at reducing daytime heat. In humid or tropical climates, shading from vegetation, tree canopies, and permeable surfaces that allow evapotranspiration may provide more significant relief. Finally, strategic placement is crucial. Interventions should target areas where heat exposure is highest, such as busy streets, transit stops, playgrounds, and open public spaces. By carefully considering durability, cost, climate, visual comfort, and placement, material-based strategies can meaningfully reduce urban temperatures and improve the overall thermal environment for residents and visitors. The physical arrangement of buildings, streets, and open spaces, commonly referred to as urban form or geometry, plays a central role in determining how heat is trapped and released in cities, as well as how air moves through urban areas. Narrow streets lined with tall buildings create what are known as urban canyons, where sunlight is blocked at lower levels and heat becomes trapped between closely spaced structures. These canyons restrict natural airflow, reduce wind penetration, and prevent efficient cooling, leading to elevated temperatures at street level that can exacerbate pedestrian discomfort and prolong the effects of the urban heat island. Urban planners can mitigate these effects by optimizing building spacing and street orientation to improve ventilation. Wider streets, carefully positioned gaps between buildings, and alignment of streets with prevailing wind directions can accelerate air movement, carrying heat away from dense areas and promoting faster surface cooling. The sky view factor, which measures how much of the sky is visible from the ground, also influences solar exposure and thermal radiation. Streets and plazas with higher sky view factors receive more sunlight during the day but also lose heat more effectively at night, while areas with lower sky view factors may trap heat and delay cooling. Thoughtful urban planning at both the block and neighborhood scales allows designers to balance solar access, wind flow, and shading. For example, staggered building heights, open courtyards, and strategically located green corridors can improve airflow and reduce localized heat accumulation. These design considerations not only enhance pedestrian comfort by lowering temperatures at human height but also contribute to neighborhood-scale thermal regulation, creating more resilient and livable urban environments capable of withstanding heat waves and rising temperatures. Architectural shading is a highly effective strategy for reducing urban heat at the pedestrian level, as it directly limits the amount of solar radiation that reaches streets, sidewalks, and open public spaces. Common shading elements include overhangs, arcades, pergolas, building projections, and covered walkways, all of which can block direct sunlight during the hottest parts of the day. By preventing surfaces from heating excessively, these features reduce radiant heat exposure for pedestrians, cyclists, and outdoor workers, improving thermal comfort and encouraging outdoor activity even during periods of high solar intensity. Even relatively modest shading interventions can have meaningful impacts. For example, a simple overhang above a bus stop or an arcade along a commercial street can lower surface and air temperatures by several degrees Celsius, making waiting areas or pedestrian routes noticeably cooler and more comfortable. When combined with trees, green walls, or green roofs, architectural shading creates layered cooling effects, where both the built structure and vegetation contribute to reducing heat. The combination of physical shade and evapotranspirative cooling from plants can significantly lower daytime temperatures at human scale, reducing heat stress and perceived temperature. In addition to comfort benefits, architectural shading can enhance energy efficiency by limiting heat absorption in building facades, which reduces the need for indoor air conditioning. Thoughtful integration of shading within urban design also contributes to aesthetic appeal, encourages street-level activity, and strengthens resilience to heat waves. By strategically positioning shaded areas along pedestrian corridors, public squares, and transit hubs, cities can create continuous networks of cool microclimates, improving both public health and the overall livability of urban environments. Water is a highly effective natural cooling agent in urban environments due to its ability to absorb heat and reduce air temperature through evaporation. When sunlight strikes water surfaces, some of the energy is used to evaporate water rather than heating the surrounding air or surfaces, creating a cooling effect that can significantly improve local thermal comfort. Urban water features such as fountains, ponds, shallow channels, misting systems, and decorative water walls provide localized cooling in plazas, pedestrian streets, and public squares. These features not only lower air and surface temperatures but also create visually appealing and inviting spaces for people to gather, rest, and socialize, enhancing both comfort and urban livability. Larger bodies of water, such as urban lakes, rivers, wetlands, or restored streams, can influence temperatures at a broader, neighborhood scale. Their thermal inertia allows them to absorb heat during the day and release it more slowly at night, moderating the urban heat island effect across entire districts. When combined with vegetation, such as trees along waterfronts or green roofs adjacent to ponds, the cooling effect is amplified. The interaction of evaporative cooling from water with shading and transpiration from plants increases the intensity and spatial range of cooling, producing more comfortable microclimates for residents and visitors. Beyond thermal benefits, water-based interventions enhance biodiversity, provide habitats for urban wildlife, support recreational opportunities, and contribute to psychological well-being by creating calming and aesthetically pleasing environments. By carefully integrating water features with vegetation and urban design, cities can achieve multiple benefits, including cooling, improved air quality, recreational value, and enhanced overall urban quality of life. Water-based cooling strategies are effective for reducing local temperatures, but they have several limitations that need to be considered in urban planning. The primary cooling mechanism, evaporation, adds moisture to the air, which can increase humidity and reduce thermal comfort in already humid climates. High humidity slows nighttime cooling because moist air retains heat, limiting the effectiveness of water features during warm evenings. Practical challenges include the need for regular maintenance, energy for pumps or misting systems, and careful management of water resources to avoid excessive consumption. Poorly maintained or stagnant water can create health risks, such as mosquito breeding or algae growth, and may generate unpleasant odors. Water interventions generally provide localized cooling, affecting plazas, streets, or small open spaces rather than citywide temperatures. Therefore, they are most effective when combined with vegetation, reflective materials, and optimized urban design, creating synergistic cooling effects and improving comfort across multiple urban scales. The Humidex Index is a valuable tool for quantifying how hot it feels to humans by combining two key meteorological factors, air temperature and dew point. This index accounts for both heat and humidity, providing a more accurate measure of human thermal perception than air temperature alone. High Humidex values indicate heat stress, signaling conditions where people are at increased risk of discomfort, dehydration, and heat-related illnesses. In urban areas, water-based cooling strategies, such as fountains, ponds, and misting systems, can lower surface and air temperatures locally. However, in humid climates, these interventions may paradoxically reduce thermal comfort, because added moisture raises the apparent temperature experienced by humans. By applying the Humidex Index, urban planners and designers can assess the true effectiveness of cooling measures, guide the strategic placement of water features, and prioritize areas where human exposure to heat stress is greatest. Proper use of Humidex supports informed decisions that improve pedestrian comfort and public health in hot urban environments. Integrated strategies combining vegetation, reflective materials, ventilation corridors, shading, and water produce synergistic cooling, reducing daytime and nighttime temperatures, optimizing street and neighborhood scale comfort, lowering energy demand, and strengthening resilience. Local microclimate assessment ensures interventions are applied effectively where needed. Effective urban cooling requires a combination of strategies. Vegetation provides shading and evapotranspiration, reflective materials reduce heat absorption, urban form encourages airflow, and water features provide localized cooling. Integration ensures cumulative benefits, improving thermal comfort, public health, energy efficiency, and urban sustainability. Implementing these strategies is essential for climate-adaptive, resilient, and livable cities, preparing urban areas for rising temperatures and enhancing quality of life.